Okay, so last time we introduced this this thing about z of g being the generating functional. Sorry, it is a generating functional of correlation functions, and log of zj would be a generating functional of the connected correlation functions, right? So where were we? So the definition of z of j, maybe I write down separately. Fresh. So definition of z of j was that it is the expectation value of trace e to the power minus h by t, and then the contour okay, is this that was the definition we get we gave last time, and then I think I didn't quite emphasize this, so let me just redo it. And so I think I just, when I was going through my lectures, so when I do this, right, then it becomes of course the expectation value of trace e to the power minus h by t ec, then e to the power x h p. Maybe I call it T1 to distinguish it from T1, and this is T1 then. Okay, so that is what it will be. That's obvious if I take a functional differentiation, where this is at time T1, of course. All right, and this is integrated, and so that's obvious. If I take a functional differentiation, that is what we'll get. But what is this actually? This diagrammatically will involve all kinds of contraction if I write it down, right? And it will involve all possible diagrams. And these diagrams are of two kinds. One will be of this kind, and then also the other ones would be of this kind now. See, in the presence of a source J, you can have, of course, but then there will be one, just insertion. Sorry, I said that I would give a cross. So this would be denoted by a cross, by a dot, and these are the insertions J that you're integrating over. Okay, the J's are always being integrated over. So here you have actually these class of diagrams, right? Not only one point function by this. And therefore, of course, I mean, I said this in the last class as an expected that you have to divide by the expectation value of one, but it didn't say it explicitly. Now, these things are nothing but z of j itself, right? If I expand z of j, it will be all kind of these diagrams, which will involve this, for example, and also this, right? If I have a lambda x cube theory. So it will have all possible such diagrams, and all of this together would make z of j itself, right? And so therefore, if I divide by z of j, if I divide 1 over zj times delta so I will get only these class of diagrams, right? And not this other class. And this is explicitly the expectation value of x at t1, right? This is expectation. All right, so I get this only. And so this one is not being integrated over, on all the crosses are also being integrated for position. So there is, because there's an integration over t, you have to integrate over the positions of this j's, right? So now you see that the way I put it in the last class is that if you take the expectation value of anything, you have to normalize it by the expectation value of 1, which is correct also, and this which gives you the z of j essentially. So now, then I said in the last class, if you try to now do delta 2z j by delta jt1 times delta jt2, okay, there are, of course, some factors I forgot to write again, which is minus I h bar and this I by h bar. So what will this entail, right? this will, okay, suppose if I do not do this 1 over Zj, this will entail, as I showed last time, would entail these kind of diagrams. Sorry, 1, 2, which I'm not integrating over. And then, of course, 1, 2 with vertex like this, and then things like that, right? It will entail all kinds of diagrams. It will entail these two kinds of things, right? And then, okay, if I do also 1 over Zj, because what it does is that it cuts over the other class of diagrams, which are simply this. This gets canceled out when I divide by Z of j, okay? Right? And then I showed you that but instead, if I do minus I h bar square delta log Z j delta jt1 delta jt2, right? I only get connected 2-point functions. I only get these two diagrams, right? This would be the sum over all connected diagrams of this kind. So these will be diagrams of this kind only. 1, 2, and then all possibilities with arbitrary number of insertions and loops, whatnot. So all of these are included. So this would be all the sum over all possible such connected diagrams of this kind. Okay. So this is something that we did last time. I don't want to repeat it, because what we showed is that if I now, this is equivalent to taking this. So this is basically equivalent to doing minus I h bar square delta 2 Zj delta jt1 delta jt2 by 1 over Zj and then minus of delta Zj delta jt1 1 over Zj delta Zj delta jt2 1 over Zj. Okay, so this is this simple algebra that if you do this, you get this, and these two terms will subtract out these class of diagrams will get subtracted out. And then we followed through the logic, and we also showed that if you do minus I h bar cube delta cube log Zj delta jt1 delta jt2 delta jt3, if I do this, then again I get only connected 3-point functions, only connected 3-point functions. Again, I'm not going to repeat the proof because I did it last time. I'm not going to redo it. So the question is, then the point is that the log Zj is actually a generating functional of connected correlation functions. Right? That's a statement then. So if you want to generalize this to all orders, so this is something that we wanted to prove. Okay, this is something that we wanted to prove last time, and we didn't complete the proof, and today I want to do that. And then in order to prove it, so please stop me if any of the statements is not clear, and especially Priyanka, because Priyanka is in charge of making these notes, so of these parts of the lectures, Priyanka and Atanu together. So Priyanka, everything is fine up to here? Did you follow everything? Up to here only? So Priyanka has somehow, oh, she's somehow disconnected. Okay, so then, all right. So anyways, so Shriram and Madhav, everything is fine up to here, I guess. Shriram, what about you? Everything fine up to here? Did you follow up to here?
I have a few lectures to catch up actually. So
oh, that's
yeah. I think like by tonight I should be able to do it.
Okay, you should catch up because this is not an easy subject, unfortunately.
Yes.
So yeah, and I cannot make it easy because it is what it is. I mean, it's not an easy subject, so you should try to catch up. Anyway, yes, so this is up to here. yeah, I hope you, at least you followed some of the things for now. So okay, thanks. So what we need to show is that this partition function z of j, which is essentially sum over all such diagrams, right? And here you are integrating over all of these j's with this. So z of j is often also called, I think, u infinity minus infinity in the presence of j, because what is happening is that you are basically changing v to v minus jt xt, right? That is, or oh, sorry, if you want to put it as, oh, sorry, v just changed to v minus j. Yeah, that's the best way to put it. So that is the change that you're doing. So it's basically, it is a change of the because we're just simply including additional vertices, which are simply these crosses indicate j's, and they send out one x to be pair. So there's only one x leg that you can weak contract with any vertex. So that is this this thing. Okay, so that's all. So that therefore it's a very nice notation. So it's a sum over all possible diagrams, and what you need to do is to show that it is an exponent of all connected. So essentially, P of j would be sum over both these kind of diagrams plus disconnected ones. So it will be not only, it will be this. So one element of z of j, which has, for example, if I do an expansion in j, then if there are 5 vertices, 5 j vertices, then this is one contribution. But in connected diagrams, you can only have some 5 vertices would only be something like this, sorry. Yeah, so this is a possibility with 5 vertices, a connected diagram with 5 vertices. Only these kind of diagrams would, so Wj, so this would be equal to Wj. Wj would be only sum over connected diagrams. So this is the statement, because when we take a differentiation of z of j with respect to j, then a differentiation will simply change a cross to a circle with the insertion 1, which you're not integrating over, and then you get correlation functions if you do it this way. And then if you divide by 1 over zj, you get the correlation function, of course. So if you take delta cube zj, z schematically, del j1, delta j2, delta j3, and 1 over zj, then you will get a 3-point function, which is not connected. We also get disconnected contributions. But if you take delta cube j, right? Now, if you take delta cube j, delta j1, delta j2, delta j3, then you will get only connected correlation functions of this kind. You can take, so it will be 3 of them will be replaced by three circles, and then you get these are the j insertions which are possible because this is in the. So what you have to remember, this is a correlation function again in the presence of a source tree. So this is what I denoted last time as schematically as G1, 2, 3, but now in the presence of a source J. It's a functional of the source J because you have to take into account all the J or to J's to all other. So in the end, we can of course take J is equal to 0. Then that would, but for the moment we can keep J. Okay. So this is a statement that if you prove that indeed z of j is exponent of all connected diagrams, then we are done, because then it is sufficient to show that that w of j is a generating functional. This statement that I made earlier, where did it go? Yeah. This statement, w of j equals log zj, that is the generating functional of the, generating functional, what I wrote, I should write it as a generating functional, if you wish, generating functional of all connected correlation function. So that's the statement that I want to show. So I can prove the statement if I can show that if I can show that W of J is simply sum over all connected diagrams. So let's then prove this statement that, sorry. So to prove Z of J is exponent of all connected diagrams, right? Which means that W of J is the sum over all connected diagrams. So this is what we need to prove. So let's see how the proof will go. So this is something I started last time, but I realized that I confused notations and I didn't do it properly. So I mean, I didn't use very good notations. So I'm going to redo it. And the proof is not that hard, it's quite simple. So the point is to see it, we have to see. So if we take Z of J, what are the kind of diagrams that can occur? So take any disconnected diagram. Right. Now let us take a simple case first. So suppose, so it will have any disconnected diagram will have certain connected components. It will have so let us call this diagram D. So it will have NCD connected components. And now the thing is that each connected component can also be repeated certain number of times, right? Each connected component can also be repeated some number of times. So let us say that it has, so let each connect, so we can somehow index, so let us index all connected diagrams. Okay, let us index all connected diagrams, DCR with index R. For example, for the quantum harmonic oscillator, there is only one connected diagram, which is the problem 3 of the assignment that we are doing now, and which is simply this. That's the only possible connected diagram. So let us index all connected diagrams DRC with the index R. So all these are only connected now. So each diagram R, each connected diagram R is repeated NR D times in D, right? And therefore, therefore, basically, NCD, number of connected components in D, would be simply sum R in RD, right? Because if there are, so there will be, most of this R would be, NR would be 0, because many connected diagrams will not even appear in D. But so let us give an example and make this notation clear. So take a connected diagram of this kind. Let us make life simple, something like this. And so this is a connected diagram D, and it has this two. It's NCD is 2. That it has 2 connected components. And suppose this is some R is equal to 1, and this is R is equal to, say, 5 in some way of indexing all the connected diagrams. This indexing is pretty irrelevant. But then this NR, so NR is equal to 1, D is equal to 1, and NR is equal to 5, D is equal to 1, right? But now suppose you take this diagram D, which has these connected component repeated twice, right? In this case, you will have NCD to be equal to 3, and NR is equal to 1D to be equal to 2, and NR is equal to 3D equals to 1. Right? So you have this connected component repeated twice, and these connected component repeated only once. So that would be the index. So now all that we need to do to prove the theorem, we simply need to account for the what I call the symmetry factor of D with arbitrary number of connected components and repeated arbitrary number of times. So if we can just simply, it's a matter of combinatorics. We have to simply take into account the symmetry factor. Once we know the symmetry factor, we can then show that if I take an exponent, I'll be able to reproduce the correct symmetry factor for this disconnected diagram. So that's the idea of the proof. So now let us try to then make this idea into practice, and how do we proceed with that? Okay, so for that, let us start with something simple. Let us start with the first class of diagram here. Okay, so one important thing is to realize that whenever you have this process, you are integrating over this process, right? You are not, so they are being integrated over. So that has to be kept in mind, which is very important. So now what is happening is when I, so what you have to do is to evaluate these objects. I already told you the notation. What I mean by this simply means the thermal average with the exact Hamiltonian, and everything is in the Heisenberg picture, blah blah blah, with respect to. So when I do this thermal this thing of XHT, right? So what is happening is that so you see that I'm going to get with every j, right? If there are, say, n crosses, if there are n crosses, so here n is equal to 5, right? Total. Okay, now I have to invent another notation. There's so many. That's the difficulty. The thing is just simply to keep track of this. So let me call it nj, right, of d. The number of times the crosses appear in this. So njd is simply 5, right? So if there's a 5, then because it comes with I to the I by h bar, so here it doesn't what we simply need to do is to compute this overall factor, forget I. So there is 1 over factorial 5. It will come, so it will automatically give 1 over factorial 5. Because when you expand the exponent, it will come with, so there'll be 5j vertices, right? And 5j vertices will have 1 over factorial 5. And then you are doing weak contraction. So then we have to account for that. So that's one thing. And then this is something that we already computed last time, is that in this 1 over factorial 5, we have to, in the first diagram, 2 of them goes, right? There are 2 of them goes here and 3 of them goes here. So the way I should compute is that, so first of all, I should have 5 C2, and then then only 3 remains. So then there is a 3 C3, because there is nothing more to compute. So then, and this is nothing but equal to 1 over factorial 5, and then factorial 5, factorial 2, factorial 3, and this is 1. So this is nothing but 1 over factorial 2, factorial 3. So we can repeat this example, this type of example. Again, let us try to stick to this kind of an example. Simple examples. Okay, so there are 3 different diagrams again. And now we have how many vertices? We have 2 plus 3 plus 3, 8 vertices. So then I should have 1 over factorial 8. And then I have to choose 2 of them here, right? If I choose 2 of them here, I will get 8C2. And then there are 6 remaining. And out of the 6, I have to choose 3 again. And out of remaining 3 will go here. So this is a trivial one. And this, of course, is nothing but, sorry, this is nothing but 1 over factorial 2, 1 over factorial 3 times 1 over factorial 3. So in general, what you see is that you will simply get the factorial of the nj's only, right? So one of the things that you easily see that the symmetry factor, if you wish, the symmetry factor is what remains after you. The symmetry factor only with respect to j's, only. is simply 1 over pi nrj factorial, right? Pi r, because r is a number of connected diagrams, and each connected diagrams will have, I don't know if I how do I nj? Oh, sorry. Let me try to nj of. This is a difficulty with this proof because it just needs to have the right notation. So nj of each connected component. Okay, this is so this is the symmetry factor with respect to j. Okay, you understand this? So so here it is 1 over factor. So here you have 3 connected components, and each connected components has a number of j's associated with each connected component, and you take a pi of that. Okay. So this is the symmetry factor with respect to j. Now there is, of course, you must have remembered there's also other symmetry factors with, say, number of v insertions, right? So with number of v insertions, of course, you have a similar thing, because suppose you have suppose you have like how many v's here are there. So here we have one. How many v's are there? This is a v vertex. This is a one vertex. So this has 3 v vertices, and this is another v vertex. So again, you have to make a choice of putting the number of v's in this diagram and number of v's in that diagram, right? And so now with respect to this, so let's number of v's, 1 second, and so you have to make a choice there. 1 second, and so oh, sorry, no, with the v's you don't need to worry at all. 1 second, because one moment. Maybe I am also doing the proof slightly wrongly. So first of all, maybe I think there's probably a more elegant way of doing this, because right. Right. Wait, let me think. I'm missing something very stupid. So if there are, we have how many vertices here? 1, 2. The total number of vertices are v vertices, and v will be equal to, in this diagram, 1, 2, 3, 4. And we can permute all of these vertices among themselves, but not all permutations give rise to the same diagram. So there's certain number of permutations which will give rise to same diagram, which will be the symmetry factor of that diagram. But first of all, I have to make a okay. No. Well, okay. No, what I was saying is perfectly correct. Sorry, I was just simply getting stupid. So okay, now comes the important point. Okay, let us now compute the v permutations, right? So with respect to v permutations, there is a slightly trick. Okay, there's an interesting trick that happens. So with respect to the v permutations, if you do the same logic, so let's say the number of v vertices is nv. I do a similar notation, nd, right? So right, and this is the notation that I put in. So with this notation, I would also get the symmetry factor with respect to this v insertions. So again, with every v insertion, you remember there is an overall 1 over factorial nv, right? But then, okay, let us see, for example, for this diagram. Okay, so let me explain with this diagram again. Let me draw it in a separate page. Yeah. Okay, so this is so now if with respect to this insertion, the V insertions, there are 1, 2, 3, 4 V insertions, and there is no V insertion here. So there's an overall factor of 1 over factorial 4. And then there is an, out of this 4, I choose 1 here, and then 3 remains, and I choose 3C3. So naively, you would think that the insertion is simply 1 over factorial 4 into factorial 4 by factorial 1, factorial 3, and then 1. So it will be basically 1 factorial 1, 1 factorial 3, right? But now what goes wrong with this is that there are certain permutations inside this diagram. If you simply permute 2, 3, 4 vertices amongst themselves, they don't give you new diagrams, right? And how many such permutations? So any cyclic rotation will not give you a new diagram, right? And that's easy to see because so you will get the same diagram that many times. And therefore, what you have to do, you have to then multiply this by 3. And this is something that you can also do by counting. If you see, so for example, okay, let's do it again like this. So suppose you had 3 here, and 3 here, and 3 here, right? And let us try to count how many contractions you get. So number of contractions you get is with the first vertex, there is a 1 over factorial 3, and then actually I leave it to do it for yourself. Actually, just try to do it on your own. So there's a 1 over factorial 3 that comes with every vertex. If you remember, that is, we defined it like this, and then you have to simply count how many contractions you can have. But it's very easy to see that without going through that logic, I mean that explicit counting, that you have to simply count the number of contractions that will give you the same diagram, right? So you will get the same diagram repeatedly by doing different kinds of contractions, right? And you have to just count that. So every time every time there is a rotation, you get the same diagram. It's not different diagram. So the diagram has a symmetry, explicit symmetry, and therefore I leave it to you to check it out. It's very easy that you will get 1 over factorial 3 into 3. There's an extra factor of 3, which is basically that comes in, that is coming in, and therefore this has to do with 1 over factorial 1 and 1 over factorial 3 into 3, right? However, here is the important thing to note is that the symmetry factor that comes here is simply the symmetry factor of this individual diagram, right? So even when there are V vertices, I can write it as pi 1 over, sorry, the symmetry factor is simply 1 over pi S dr c pi r. So that is going to be the symmetry factor, where SDRC is the symmetry factor, which is half of this disconnected diagram itself. So essentially, with respect to V, you are simply summing over each diagram. The symmetry factor is simply the product of the symmetry factor of each individual components, right? Up to here, you're fine? Okay, just think over it. So the symmetry factors has to, the overall symmetry factor is like this. So far that we have got is 1 over pi nj dr c and pi r times s dr c. Okay, and that would be the symmetry factor of overall symmetry factor of D, right? However, this is wrong. This is true, but this is true only if each connected component appears once. So what is a symmetry factor actually? Symmetry factor tells you the same number of time a same diagram will appear, right? If you, all kinds of weak contractions will give you the same diagram. And because you're integrating over, right? Because you're integrating over these vertices, whether 2, 3, 4, And because or 3, 2, 4, it doesn't matter, because all of these would give you the same diagram, right? But then there are certain permutations of the diagram that will give you if there are some additional symmetry of the diagram itself, then there is additional number of times the diagram will appear. So that is this is symmetry factor, because you're integrating over, so you're just simply counting. And that's the same thing as actually explicitly computing number of weak contractions you get, right? So that's very easy to see. They're the same thing. I mean, if you realize that, it's essentially the same thing, because you can go back to the earlier lectures, and if you don't understand this, we will discuss it again, definitely. But please, if you don't understand, ask me in the next class, this factor. But just think it over, and so the symmetry, so this is what you will get, okay? So you have to simply count the number of times. However, if suppose a connected suppose now a connected component appears twice, then what to do? Suppose you have this thing. Now what goes wrong? And then actually it doesn't matter, the distinction between J and V doesn't matter at all. Let us say this component appears twice and this component appears twice. So what you can do, now it is very easy to see, you can simply permute 1, 2, 3, 4, for example. You can simply take, you can literally permute one, you can just one with 3 and 1 with 3 and 2 with 4, right? So if as a whole 1, 2 can be transposed to 3, 4. Now suppose that it appears thrice, like 5, 6. Then what you can do, you can as a whole, you can take 1, 2 to 3, 4, 3, 4 to 5, 6, and 5, 6 to 1, 2. So number of additional permutation, the additional symmetry factor, is simply the permutations within the diagram, which is simply pi nr d factorial, right? Pi r. So you have to simply multiply it by the number of times each diagram is appearing, because as a whole, you can just permute identical diagrams. So you can take 1, 2 and you interchange with 3, 4. 3, 4 you can interchange with 5, 6, and 5, 6 with 1, 2. As a whole, you can just simply take and permute amongst themselves. So you would get repeated copies of these diagrams, and they are indistinguishable. So basically, you have to see all kinds of weak contractions that give rise to the same diagram. And if you're integrating over the vertex, that vertex 1, 2 is simply a dummy variable, so it cannot be different. So you just simply have to compute the number of times you're getting the same diagram with weak contractions, as simple as that. And that gives you the overall symmetry factor. And that's actually is independent of the fact how you're actually normalizing vertices, whether you're taking 1 over factorial 3 or not. It's a rather simple thing. It's simply a consequence of the Week's theorem, simply counting number of times, number of permutations, number of contractions that you have to do. And you simply, and if the contractions give you the same diagram, because you're integrating over the vertices. So of course, if you have explicitly a one vertex, you're not integrating it over, then it's different, right? Then you cannot, then this diagram 1, 2 is different diagram, right? Compared to say 1, 2, 3 and 3, 1, 2 are not the same diagram, because they're rotated versions or some kind of versions of each other, but anyway, so the point is that these two are not necessarily the same diagram. However, if we're integrating over these vertices, then they're the same diagram, because these are dummy variables of integration. So simply see how many times, if you do weak contraction, how many times you're repeatedly getting the same diagram. And that would be the overall symmetry factor. So you see that then the overall symmetry factor of D, so in generally, overall symmetry factor of D would be equal to 1 over pi r nrd factorial times pi, sorry, I forgot to do a factorial here, nj d sorry, I should have written DRC because so I'm taking the number of times each connected component appears in the diagram D, right? That is how I define it. And Nj is the number of j vertices in each connected component. And okay, so now if it appears nr number of times, right, then it has to be, sorry, let me, I should write it in two different lines, is equal to 1 by pi r equals to pi r, let me put it this way, nr drc factorial times 1 by pi r, and then nj drc factorial and sd, just with the v vertices, sd rc, right? And then the whole should be multiplied by nr drc, because it is going to be, if it appears several nr number of times, it has to be multiplied by this time, right? So this is going to be the overall symmetry factor of D. That's all we need to see. So now what I'm going to do, now if I, so then I can claim, then clearly, okay, now suppose, okay, let me again suppose the number of connected components, just for of course, the number of connected components are not finite. Suppose there can be only, say, 3 possible connected diagrams, or we take only 3 possible connected diagrams. Or okay, suppose, okay, now consider, okay, let me see. Maybe it's better to put it right this way. Consider 3 connected diagrams and see how many disconnected diagrams we can generate with them, and whether it has the right. And let us call this connected diagrams X, Y, and Z. Okay, give them some name, X, Y, and Z. So what I would do now is to I would define something called X tilde. X tilde will be X divided by the symmetry factor of this connected diagram, X S dx, right? And number of times J appears in X, okay? Factorial. I will do this. And similarly, I will define Y tilde equals to Y by S dy times Nj Y factorial, and Z tilde is equal to Z by S dz Nj Z factorial. Okay. Now look at the following series. So let me look at the following thing. Let us look at let us look at the following expression: e to the power x tilde, e to the power y tilde, e to the power z tilde. Right? What do I get? If I write it down, I get 1 plus x tilde plus x tilde square factorial 2 plus x tilde cube factorial 3, and so forth, and 1 plus y tilde, similarly y tilde square by factorial 2 plus y tilde square by factorial 3, plus so and so forth, and 1 plus z tilde plus z tilde square by factorial 2 plus z tilde cube, cube by factorial 3, so and so forth. So now let us look at any element of it. So this would be basically then x to the power, say, k, I get, but x to the power k would come with k factorial, right? Some k, and then I will get y tilde k, l, k lm with l factorial, and then z tilde m with m factorial. That is what I will get, right? Now, if you compare with the symmetry factor of such a disconnected diagram, you see you exactly get that, because this is a symmetry factor that's already absorbed in x tilde, y tilde, z tilde. And then we have this extra nr thing, right? And this is exactly the number of times each connected component is appearing. So you are correct, and this correctly reproduces the symmetry factor of D having K times X tilde, L times Y tilde, and M times Z tilde. Okay, so it's exactly the right symmetry factors that you should get in this, because here X is this connected component X is being repeated K times, this connected component L times and M times, and you get the right combinations by doing this multiplication. So therefore, but now, and this you can repeat with arbitrary number of connected components, right? So we have only looked for 3 connected components, but you can now take arbitrary number of these if you wish, and therefore it's quite clear that it's clear that we can extend to all connected diagrams, but to all connected diagrams, because we're only taking 3 of them here, and therefore e to the power, so z of j has to be then equal to pi of e to the power each connected component, like which I can call, let's call as this each connected component as a diagram drc, then divided by nj drc factorial times s drc, right? So this, it is simply product, and this is equal to the sum, right? E to the power sum r drc divided by nj drc factorial s drc. Okay. So it will be the, so basically what it means is that it will be the sum over this thing, right? But you see that this is the right symmetry factor of any diagram, because you see that if I have some diagram like this J12, right? J12 will appear twice with a permutation, J12 and J21, but these are not the same diagrams. So these are the same diagrams because you're integrating over 1 and 2, right? So you should always have this extra factor of nj factorial anyway. So so essentially what you get is that so this actually can be thought of as a full symmetry factor of the diagram in presence of j, right? Otherwise you simply have this factor usually. If you look at Coleman's book, Coleman has a similar way of doing the proof, but he doesn't include this. He does it in a very different way, because he takes into account, he does in a little bit more difficult way, different way, because if you look at Coleman's book, he has done it as an operator identity between normal ordered and time ordered. But here we are not doing that, because normal ordering is not useful when you're out of equilibrium. It doesn't help you to compute matrix elements. So normal ordering only helps you to compute vacuum to vacuum matrix elements. So therefore, what we are doing here is a different way of doing things. But if you do it in this way, instead of looking at operators, we are looking at diagrams directly, then we have to take into account this nj factor. So otherwise, if you read Coleman's book, my proof and his proof is very similar. So you can read Coleman's book in around, so he does this same kind of thing, same kind of similar proof, where he claims to be that z of j, but he doesn't put in the j though. He doesn't write it. Actually, he doesn't prove this thing. He proves a different identity. This is related. So at the operator level, but these are not operators. This is simply a matrix element. Anyway, so this is a proof. Okay. So then this completes the proof. But you see that when you are now taking a functional differentiation, right? So it means that W of j has to be simply sum over all connected diagrams, as I wanted to prove, nj drc factorial and s drc, right? So now suppose you take suppose I take mth derivative of this object, del j1 delta j2 delta j3 delta Jm, and I put m is equal to 0, right? Then only those diagrams, sorry, if I put j is equal to 0, then only those diagrams will contribute where nj, so if I do this, then only diagrams where, okay, so of course, when I do this, you know that we are integrating over j's, right? There, in each diagram, there are nj's, number of j's, right? In each such DRC, there are nj DRC number of j's here. So when you're differentiating with respect to j's, either I keep some j's undifferentiated, or if it has less number of j's, then it will differentiate to 0. So but then I'm putting all the j's, only diagrams where nj DRC is equal to m will contribute, right? If I take a differentiation, right? Only where diagrams where the number of j is exactly equal to m will contribute when I differentiate and I put j to 0. And therefore here, and when I do a differentiation, you see this factor actually cancels out, because again, because it's simply, right, if I take d by d xm of x to the power m, I get m factorial at x equal to 0. Sorry, here, yeah, if I put x, it doesn't matter here. But here, if I have, for example, x to the power m minus 1 with some factor, then I simply get factorial m when x is equal to 0, would give you factorial m. So then, but now I already have this 1 over factorial m here, so therefore it cancels out. And this would give me exactly the connected correlation function. So then you get the strip diagram like this, 1, 2, m, where you replace the crosses with circles, and then when you replace the crosses with circles, then you get simply those diagrams DRC, again writing schematically, but the point is that you're no longer integrating over the j's, and then you are only taking into account this. So you just get all these propagators, like the usual method that we said earlier. So you're only getting these propagators and the vertices, and that's all. So this would be without this 1 over, and this factor you don't need to take into account anymore. Okay. So that's the way things work. So this is how this is a diagrammatic proof of it. But then why we did this, right? Why we are interested in W of j, and that's the question. So W of j is a root, is a way we can access this this interesting quantity that we are talking about, this 1 PI effective action. But before I get there, is there any question about why W of j is a different generative functional or form?
I have like a doubt, like in the previous step, after the exponent of x tilde into exponent of y tilde, can you show that part once?
Yeah. Okay.
Yeah. Okay. So you're expanding the exponents and then you're generalizing it in the next line.
Exactly. Because you can think instead of x, y, z, that means w, v, whatever, several connected diagrams. But then I get simply more additions in this.
Right.
More. Yeah. It will simply factorize. So all that I need to take into account is I have to reproduce this extra symmetry factors which are here, right? That's all I need to do, and these factorize. So I just take into account. So the point is that e to the power x individually produces this right symmetry factors, this additional symmetry factors. That's all I need.
Okay.
Was that the question? No.
Okay. Yeah. So like I missed that part. Following that. Yeah.
Okay. Yeah. No. It is not easy. I mean, it looks easy, but it is certainly not. So I would. So these are difficult. Okay, that I cannot simplify this further. I'm sorry about it. I mean, but I think I hope. So I think many times I've seen people give QFT course just stating this stuff without proving them. I think you must know how they're proved. Okay, that's number one. I don't want to. Okay, I can easily finish a lot of stuff, right? But the point is not to simply know statements, but see how they're actually done and how to get the proofs. And because it's very critical to see those, to see the reasoning behind these statements, and these are not easy because these take time, and if you just read textbooks, they're often very terse. You won't understand directly from textbooks often. You can read Coleman's proof, right? He does it in a different way and little bit different, and my proof is a little bit different because he proves a different thing, not the same thing, but then he states my result as an extension but anyway, I think I'm following a different route in this lecture, so I'm not following Coleman's route. I'm just doing it in my own way. But anyway, so this is something that, but I reproduce the same result, which is correct. And anyway, so this is how it is. So it is good to know the proof and how things work out. And this is how it is. But the basic logic is very simple, right? You simply, whenever you are integrating over a vertex, you don't. So you have to count all possible diagrams without, and any permutation of the vertices will give you the same diagrams, right? But if the diagram itself has symmetry, you will generate the diagrams multiple times, right? So that's an addition to that. We have to take into account all those factors. So for example, if there was, suppose I take this diagram which has no symmetry, some horrible diagram like this, right, which has no symmetry at all, then I'm integrating over these vertices. Say whatever. Suppose I have these j vertices. Let's look at only those 3, 4, and I take 1 over factorial 4, and then if I permute these vertices, each permutation produces a different diagram. So I will have factorial 4, and there's exact cancellation, right? But now suppose I have this, right? So so now I look at a number of v vertices. Number of v vertices is equal to 3. 1 over factorial 3, and then of course if I permute factorial 3, I would get I would think that I will complete cancellation, but then there's an additional symmetry factor because I will divide by the symmetry factor, which is 2, which is 3 itself, because if I rotate the diagram by 3 times, right, in the clockwise, then I don't get then I produce the same diagram, right? So and because I'm producing the same diagram, I should be careful and say that actually this is actually have incomplete cancellation, and I have 1 over 3 as my symmetry factor. So okay, because so in this diagram, if I permuted, I got the same diagram, right? I got a different diagram, and so these two cancelled out. And the logic was that I'm integrating over each vertex, so they should not be counted again. But here, actually, the number of times I'm able to produce weak contractions are much less because the diagram itself has a symmetry, right? And so this is the why we got this also when we did this computation, we got symmetry factor half, for example, here. The same reason why, right? So you can think about it a little bit, and then if you don't understand, ask me again. You can actually, you have to just meditate on this statement and see why it is like this. I mean, so just think about it. So it's very important that you actually think about the lectures. So it takes some time to digest this. All right, so now let me move on to the 1PI effective action. And this, I said, is a very central concept. And the reason it is a very central concept in quantum field theory is that the point of the 1PI effective action, it is also called the quantum effective action. The point of this quantum effective action is that we can use this to compute correlation functions retaining only 3 diagrams. So tree diagrams are diagrams of this kind which has no, which have no. Okay, so basically one way of thinking about this quantum effective action is as follows. So W of J is a generating functional of all correlation functions, but the quantum effective action is a generating functional of all proper vertices. the proper vertices are by definition as follows. So are those, so it already takes into account or loops into effect. So let me explain this a little bit better, what I mean by this. Okay, I will make this statement. I'll make it clear. Maybe you can hold on a little bit. But before I introduce the 1P effective action, so I already told you its physical meaning in my previous lecture, the physical meaning of it. But let us try to look at more of an operational meaning for the moment, and then I will say that connected to physics. So the operational meaning of it is as follows. So think of any diagram. Any diagram, in any connected diagram. So I'm looking now at a given connected component. So any connected diagram. So now this is a tree diagram with exact propagators and proper vertices. So I will explain this first, and then we will see that the 1P effective action is essentially graphically just a generating function of proper vertices. And this is exactly the way what we should use to compute it. And then I will compute it. Okay, sorry, I need to open the door. Okay, so let me explain this, what I mean by exact propagator and proper vertices. Okay, let's try to look at this diagram, okay? All right, so now if you can think of this, just think of this part of the diagram. So I'll divide the diagram into some parts. Most of it actually is graph theory and basically also something that you might see in computer science actually. And in fact, many areas of mathematics have very similar kind of things. So you can think of this part of the diagram and then these legs. So what does it look to you? Abstractly, suppose I draw a double line now. So I can draw a double line. So this double line would be simply an abstraction of this part of the diagram, these parts of the diagram, say. So suppose I draw a double line and these double lines, right? So suppose I have a 3-point function, 3-point connected function. What is this general structure? I can have simply, so I have to simply start from this point, 1, 2, and 3, right? So if I start from this points, there's something that comes out of it, right? And there's only one line. And on this line, of course, I can have all corrections like this. And this is something I can call self-energy corrections. I'll explain that later. So this is what, I think I introduced self-energy in one of my earlier lectures as sigma. So remember the retarded pole propagator had this omega minus omega naught minus sigma, something of this structure. So this is this kind of thing. So all of that is suppose I include here, right? And I include here, then this becomes exact 2-point function, right? This is identical to taking this 1, 2 and computing it exactly. But instead of going to 2, here it will go to a point 3. Sorry, let's call it A. Let's call this B. Let's call this C, right? And now this A, B, and C is going to be joined by something I call the proper vertex, right? Now, what is the graphical definition of such a vertex? So this graphical definition, so what does this 1PI mean? 1PI means one particle irreducible. So essentially, so when I take, okay, let me denote by gamma 3 is equal to sum over all diagrams which with 3 endpoints or 3 external points. External points simply mean that here we have A, B, and C. For the moment, you can see we are not integrating them over, but later we'll integrate them over. So there are 3 external points. The sum over all diagrams with 3 external points, and which cannot be disconnected by cutting one line, right? All right, so basically an example of it will be this. This is a one particle irreducible diagram, because if I disconnect any one of the lines, the full diagram still remains connected, right? But now if I look at this diagram, A, B, and then suppose there is some extra additional vertex that I'm going to integrate over, and then this is a D, right? This is not a 1 pi. This is not 1 pi, but this is 1 pi. Because if I disconnect this, then the whole diagram gets disconnected. So this is not 1 pi. Now, the point is that if I want to look at the whole connected diagram, then I should use exact propagators and an exact vertex, which is a sum over all 1 pi thing. So this is how I can express a general 3-point. Okay. So this is a very general story. So what I can do, so now so basically any connected diagram is a tree diagram generated by 1 pi vertices gamma n. I'll explain that. And exact propagators. G, right? So that's the story. So if I take any, suppose I can do it this way. One, two, three, and then this goes into something and say this comes out. So this is a tree diagram, but here I have only 1 pi vertices, right? And these 1 pi vertices. So let us look at more complicated 1 pi diagrams, right? So A, B, C. This is also 1 pi diagram, right? Because if I cut it, I can. It still remains connected, right? This also is a 1 pi diagram. But say something like this again. Say A, B, and then sorry. Let me give you another. Yeah, let me maybe I can 1, 2, 1, 2, 3, and say here here I have here I have something like this. Yeah, this is not a 1 pi diagram, but there could be more other kind of examples of. This is not 1 pi because for one reason is simply that I can if I even if I okay, let me give you okay. No, suppose that there is this. Okay, suppose this is. Let me try to draw 4 with 4 vertices in example. So this is A, this is B. So these are where I can attach external lines, and there is a 3 vertex here that I have to keep in mind, and this, and then I have C and I have a T. There's a possibility this is a 4-point vertex. This is not 1 pi, because if I cut it, I am going to generate. So why I should not consider this? Because such diagrams, because I will be doing overcounting, right? I'm doing overcounting because I can always generate these kind of diagrams like this by considering exact propagators, because exact propagator itself would be something like this, plus this, plus this, plus something like this. So it will have all possible corrections already included here. And this is simply one of such corrections. If I include this thing, right? So this already includes this. So I don't need to reconsider it again. So, but these are 1 pi, I can retain them. Okay. So if I want to compute a 4-point function, okay, let me explain this. Suppose I'm interested to compute a 4-point function, right? So I don't need to take into account this into gamma 4, right? This is not in gamma 4, not in gamma 4. Why? Because I can also always generate it like this. This is one of the diagrams. Suppose I take exact G. If I take exact G and the 1 pi gamma 3 here and gamma 3 here and G and G and G, right? If I do this, then one of the diagrams is already here, right? So I don't, but so this that is already reproduced here. So for not double counting or multiple counting or avoid multiple counting, it is sufficient to consider only 1 pi vertices plus exact propagators. Okay. And then, of course, if you do that, you will get only finite number of diagrams. So suppose if I'm computing an endpoint function, then suppose n is equal to 4, the kind of diagrams I will get is like this, where this is gamma 4, and these are exact propagators coming from 1, 2, 3, 4, plus I can have this, which I just drew. This is gamma 3. Now, the original theory may have only, say, X cube interaction, but you can generate such arbitrary number of vertices through interactions, right? So gamma 3. So even if you have X cube, gamma it can gamma 100 could be non-trivial. Okay. So these are the possibilities, right? So 1, 2, 3, 4, and then you can have other permutations like here 1, 3, 2, 4, like that. And yeah, so these are the only possibilities. If I look for a connected endpoint function. So okay, so I should have think sufficient to go. If I look at connected endpoint functions, then it is just enough, and even disconnected ones, because each disconnected piece is simply exponent of connected pieces. That's what we already proved. So basically that's it. So this is the main reason why you can. So this is simply a graphical argument, right? And what does this physically mean? Physically, it means that whenever we're looking at tree diagrams, we're essentially looking at a classical theory, right? It's simply classical theory because it has a good classical limit. Because the loops essentially has this. So what we will show is that all loops, so number of H bars in the number of times you will have Planck constant in the vacuum only, not actually in the finite temperature. Things a little bit complicated. But if you go to vacuum correlation, if you have T is equal to 0, the number of H bars is simply related to number of loops, right? So if you have a tree diagram, there is no loop, so it is exact in H bar, right? So now if you can pretend that, so you can think that if you're working with only this 1 pi vertices, and this 1 pi vertice, and the point is that and this 1 pi effective action or the quantum effective action is also sometimes written as gamma phi, is essentially schematically just sum n is equal to 0 to infinity, then d phi. Sorry, okay, here we are talking of only x. Let's talk about x only. So it is d x1, d xn, and then there's a 1 over factorial n, and then this gamma n, right? And gamma n is a functional of actually x, x1 to xn. We'll see. So this is a proper vertex. And so this is actually, sorry, what I wrote is rubbish because it is okay. Sorry, so it's that x is equal to 0. Sorry. So it is sorry, and then you have what I'm writing. Sorry, 1 second. This is dt1 dtn. I'm really sorry about it. And then gamma. So gamma n schematically, this is gamma n, and then x of t1 times x of tn. Okay, so this is how the quantum effective action is going to look like. It's going to be an expansion of this kind, and these would be the proper vertices. So if I can extract the proper vertices from this 1p effective action, and then I can simply, so this would be something like an effective classical theory. Although there'll be h bar, and I actually wrote down the explicit answer. This will be, so this will be the effective classical theory, the whole thing, because I can simply work with tree-level diagrams without any loops with this theory, where I get the vertices from this 1pi effective, from this quantum effective action. So that's the exact logic. And now this is what tells you about renormalization. So when you talk about renormalization, essentially what it means, I think there's a very nice analogy in Coleman's book. So what you can do is to say that I take a mass and I immerse it in water, right? But if you see that, you know it from very well that because of buoyancy force, the effective mass of the thing becomes smaller, right? So if you just forget the medium and you just simply think about effect on gravity or anything external, you could as if work it as a smaller mass. And that's exactly the point. So the point is all of the classical, so you have two different descriptions. One is an effective, a microscopic description that has loops and all of this complicated stuff, all kinds of weak transformation that generates all kinds of complicated quantum effects. But now you have a simpler description, it's an effective classical theory, where you only look into tree diagrams, right? And this, okay, I forgot to tell you one thing. So you can say, how do you get this effective G from this one loop? What is it? How do you get G? So G is nothing but what I will show is equal to gamma 2 inverse, right? Schematically. So the point is gamma n is not really a simple vertex. It also has derivatives acting on this x. So it is an operator. So the way you can think of gamma n, it's not really a number, but it's an operator because it has time derivatives. It has d by dt1, d by dtn, I'll show it, which has basically momentum expansion. And this is an operator. And essentially the G is a gamma 2 inverse in the operator sense. So the exact propagator G is nothing but inverse of gamma 2, okay? So all the information that you need is in the quantum effective action, that you need to compute anything. So it has a dual meaning. So the first meaning is as follows. The first meaning of the quantum effective action is that it gives you it gives you the exact equation of motion for expectation value of x, right? That is the first meaning of it, which we're going to prove. But there's another meaning which is also very important, which we're also going to prove, is that so these gamma n's, the statement here is that the quantum effective action is a generating functional. So now if you take derivatives with respect to x, you get gamma n, right? This is generating functional of all 1pi vertices. So what it means is as follows. So effectively, if you look at this classical theory, and this, so when you're talking of when you say that you are renormalizing a theory, you basically mean that you are constructing the 1p effective action so that you can have an effective classical story. You're having an effective classical story to describe the process, forgetting quantum corrections. And then in this classical description, your original classical parameters get renormalized. They are no longer the same. Now, this has nothing to do with subtracting infinities. Actually, this can happen even in quantum mechanics, and I will show you how what is a renormalization that's happening even in quantum mechanics. So then, therefore, when you see infinities, there's a separate issue that the question is there are all kinds of infinities that are happening. So the point is what an insight of Feynman, Tomonaga, and Schwinger was that you can absorb all of these infinities only by redefinition or a similar redefinition of a finite number of physical quantities, only a finite number of parameters, and then you can then have all kind of predictions of theory. So that was the insight, but the basic thing is exactly the same. The basic statement, and there's not really any change. So if you understand this, we can understand the renormalization of effective theories. So you see there are two different things of the 1p effective action. One is it gives the equation of motion of 1p of x. The second important thing is a generating functional of the effective vertices, the physical vertices. And this is something we'll prove in the next class. And then I'll also try to, if there is time, I'll also try to work out an example. So I already showed you, I also already told you that what is the 1p effective action of the lambda x to the power 4 in the previous class. I will redo it. I think lambda x cube or x to the power 4. It's for x to the power 4. Yeah, I worked it out for x to the power 4. So I will try to work. I will show you how to work it out. And once you work it out, you're already a long way into understanding quantum field theory and renormalization. So this is the main point. So effectively, this 1p effective action can be used to compute correlation functions, to compute S matrices, to compute any damn physical observable, right? But using only a classical effective description. And therefore, this 1p effective action is a physical, has physical couplings. So then, of course, you can also do it in a very interesting way. So you say that, then the idea of renormalization group comes in, because what is often useful to do is to define an effective theory for a certain scale of resolution. So we will also see how that comes about in this business. And then, so that will not be so dramatic in quantum mechanics, but when we go to field theory, we will see that there's an effective scale that you need to take into account. So there are many different ways to define a physical constants that is depending on what scale, what's the scale of resolution of your apparatus. And depending on that, you can have different effective descriptions. But of course, if you construct any physical quantity, all these different descriptions will have the same answer, because physical quantities or physical predictions will be independent of that. So which means that there's a RG flow. There are different effective descriptions are connected to each other by some flow equation, which is the flow is simply the flow of the effective scale. And that is essentially the renormalization group, which is a very fundamental thing, because what we see is that if you go to low energies, then only a finite number of coupling constants are relevant. Even if you have infinite number of couplings, that's analog of saying in quantum mechanics, you have lambda x cube, lambda tilde x to the power 4, lambda tilde x to the power 5, all possible such things. But only only few of them are relevant to low energy physics. And in fact, we already know in low energy physics in quantum mechanics what is relevant is simply the X squared term, and all interactions are irrelevant actually, because all interactions, because if you just take a harmonic near any critical point, we already know only X squared terms matters, and that remains true also in quantum mechanics. So all of these things become irrelevant. So as long as you're interested in very, very small fluctuations, or essentially you take a system and you perturb it using very low energy, very low momentum input, and then you can describe the theory with only finite number of coupling constants. And that's the whole non-triviality. That is why quantum field theory is predictive. It simply means that at a given energy scale, even if there are infinite number of, if the actual physical theory is not quantum field theory, but say string theory or something completely different, you still doesn't matter, because for a given scale of observation, only a few things will be relevant to the physics, right? And that's the beauty of quantum field theory. So quantum field theory is inherently predictive. It shows you why it can predict nature. So that's a very fundamental. These are the fundamental things that we will slowly learn. So this is how it connects. So I'm already my idea of giving the lecture is to slowly unfurl this, because these are very difficult concepts. So I think it's good to see them in a slowly. So I'm trying to show it in quantum mechanics, because here you're already familiar, but in quantum field theory, it's exactly the same. There is nothing different because these are graphical statements, which will simply go through. So there'll be only difference would be that there will be infinities, and we have to learn how to deal with them, and some other stuff. But fundamentally, we can easily sail through, which will be, you will see that we can easily sail through in one class or two classes. So we are now going to build a groundwork, and this is how we'll approach. Okay, so now there's a seminar I have to attend. So maybe I end my class here, and I will continue from next class, where I'll give the proof that I will say what how the 1p effective action is related to W of J, and then prove that it is a generating function of all. The proof will be rather simple. and and the proof will be much simpler. It will be just taking me only 2 minutes to do it, 2 or 3 minutes. It will be much simpler than this, because all the horrible stuff was today to prove that that z of g is an exponent of all connected correlation functions. So this was very hard because we had to walk through it a little bit, although it was not that hard though, but we had to do some work. But for the other part, it's rather trivial. So then we can quickly move to the example. So tomorrow we will also compute the 1 PR effective action, tomorrow meaning on Saturday, and then you will get a complete physical picture of what is happening. Okay. All right. So that's all for today.
Hello, sir.
Yeah.
Sir, is there some PhD student in the campus? I want to discuss something.
Can I stop the recording first?